All right, let's start. Good morning, everyone. Thank you for coming to the class. So, for this week, first we will finish the concept of neural network. But we started this concept last week, and we need to explain a little bit more concepts and how it can be trained on keras. We will see today. And since many students told me because we are getting closer to the final exams and you are doing some research, PhD students, maybe it is not bad if we put today as the last day of our class and not to have a class on Thursday. Then I think maybe it's not a bad idea. Then let's consider today as the last day of our class, and then we won't have any class on Thursday. I'll be in office available for sure. There is any questions, it might help, feel free to stop by. But we won't have any class on Thursday. Today is the last day of our class, and today we will see curves of dimensionality a little bit. But as I explained before, something that we will see for curves of dimensionality in this class is just one small concept of PCA, which is used very often, but we have other techniques for reducing dimensionality that we will, if you take any course in deep learning, you will see that. So I think I have posted an announcement about the final project. Hope everything that you read is on the comment. Again, if there is any question about final project, please stop at my office. For the final project, we will be a little bit flexible about due dates, and if you need more time, please email me, but then we will see that how much we can be flexible. About the exam that we had on April the 8th, I will post your grade by end of this week. Then I try my best to post the grades by end of this week. Then again, if there is any question about your grades for that exam, I'll be in the office. Then today is the last day of our class. We won't have class on Thursday. About the final project I explained. And today we will finish this concept of multi-layer perceptron. We will see a little bit more about keras, and we will see a little bit about curves of dimensionality. And only available after the class if there is any questions. Okay, so what we did up to now, as we explained, concept of perceptron first was established in 1950s, and the goal was to combine two concepts, concept of activation and concept of linearity. As we explained, every perceptron consists of two parts, activation and linearity, and as we explained, we have different functions which can be used for activations. Among them, some of them are very popular, ReLU for example, LU for example, sigmoid for example, tanh for example. And as we explained, if you do not consider an activation on perceptron, it means that you have just a linear model. And perceptron with linearity and activation is a new concept comparing to the linear models. Then as we explained, if we want to use perceptron for classification, there are some data sets which cannot be classified into two classes by considering just one line, because as we explained, every perceptron gives us just one line. And if you want to have just one line, for example, data set like this cannot be split into two classes. Therefore, more perceptron is needed. And as we explained on Thursday, if you consider, for example, two perceptrons, let's see, these are input. I'm considering two perceptrons. If you consider two perceptrons, then you can get two lines. And by using these two lines, you can split your data set into two subsets. Here, as you can see, this region gives us one region, and outside of these two lines, we have another region. And as you can see, these points can be split into two classes very nicely by considering two perceptrons. Okay, this is, I think, the last thing that we had on Thursday, theoretically wise. And also, we explained about keras. and today we want to continue a little bit more about Keras. As we explained, Keras is one package that we have on Python. It can be used in deep learning stuff, and it is used very often for deep learning stuff. Then I have also explained about training one model. Here, if we want to have, for example, a neural network with two hidden layers, and in each layer we can assign how many neurons we have. For example, here the first layer there are 300 neurons. In the second layer we have 100 neurons. Okay, let me explain a little bit about the theory of these multiple layers models, then we will come back to this. And I have posted this on Carmen, then please feel free to run these. In the class, we do not do this because it takes time, not too time consuming, but please do it at home, and please try to play some games like changing the number of neurons, changing the activations. And today I will explain a little bit about compiling, and for compiling again you can play lots of games. Okay, so then multi-layer perceptron. As we explained, when we have one perceptron, it means that you just want to have one line. If you want to have two lines, then more than one perceptron is needed. As we explained, by considering two perceptrons, we can have two lines. What about if we want to have more than one perceptrons, more than one layer? Because if we come back to this model here, as you can see, we have just one layer. I'm talking about hidden layer. This is the input layer, this guy is output layer, and here we have just one hidden layer. But what about if we want to have more than one hidden layer? This kind of model are called multi-layer perceptron. It means that you have perceptron, one perceptron, you can have one layer with more than one perceptron, and now we want to have more than one layer. It is abbreviated by MLP, is a type of artificial neural network that consists of multiple layers of nodes, where each node is a mathematical function that takes a set of inputs, perform a calculation, and produce an output. So the first layer of MLP, as we explained before, is called the input layer, and it receives the input data. As we explained, there are just two layers that are connected to the outside world: input layer and output layer. Whatever that you have as the hidden layer, which are in the middle of input and output, they are not connected to the outside layer, to the outside. They just connect to the layers which belong to the model. So the last layer, as we explained, is called output layer. The first layer is called input layer, and and the last layer, which is the output layer, it produces the final output of the network. For example, in the previous example that we had, the last layer, which was output layer, here we are producing y hat. And here, as you can see, y hat that you get are these values, -1 and +1. It means the values which are produced by y hat can have one of these numbers, -1, +1. Okay? Makes sense? Makes sense. I believe if you understand the concept of sine function, it is clear, because you can see that y hat is defined as sine of this summation. Therefore, here, since sine can output, we can output just -1 and +1 by using sine function. So that's clear. Okay, so the layers that we have in between, as we explained before, are called hidden layer, and they perform computation on the input data. It means you start by input values, then input values will be sent to the hidden layer. We can have multi-hidden layers, and after that, these informations will be sent to the output layer, and in the output layer, we will get the output values. In the previous example that we had, input layer consists of just one neuron, but you can have input layer which consists of more than one neuron, and we will see one example today on Keras. Each node in the hidden layer receives inputs from all nodes in the previous layer. This is very important to understand. These kind of models that we are learning in this class are called fully connected. The reason that these models are called fully connected comes from this fact, that as you can see, every layer will receive information from all neurons in the previous network. And see, For example, if you consider this guy, it is one neuron. This neuron is receiving information from all neurons from the previous layer. See, that's the reason that this neuron, this model is called fully connected. I think fully connected is a very nice name. Makes sense why it's called fully connected? Because this every neuron in one hidden layer receive information from all neurons from the previous network. See? In 2014, one model which was given, we had one paper was published, the name of paper was that dropout. Dropout was one model which was given to reduce the regularization. And when they wanted to reduce, when we say that reducing regularization, it means that they wanted to reduce the volumes. Then one way that they could reduce was that instead of considering all, let's consider some of neurons. And by using some techniques, we choose some of them and some of them will be considered in every part. Then a little bit beyond the border of this class, okay? But I just want to tell you that what people do, but something that we do here when we say that fully connected, it means that every neuron that you consider in hidden layer will receive information from all neurons from the previous layer. That's the reason that these models that we are learning are called fully connected. Therefore, each node in the hidden layer receives input from all inputs, from all nodes in the previous layer. And this neuron does exactly the same thing. It does produce an output that is sent to all neurons in the next layer. Make sense? And one more time, I'm sorry. Okay, here as you can see, this guy, for example, will receive information from all neurons in the previous layer, and this guy will send information to all layers in the next layer, all neurons in the next layer. They're receiving information from all neurons in the previous layer and will send information to all neurons in the next layer. It is actually the foundation of these models. Okay, so the output of a node is typically passed through a nonlinear activation, as we explained before, which introduces nonlinearity into the network and enable it to a model complex relation in the data. As we explained, every neuron that we have here, see, when you accept these guys, which are input, all of these neurons that we have here, all of them consist of linearity activation. When you consider these circles that we have here, all these circles that we have here consist of two parts, linearity and activation. Therefore, if you want to use the name which was historically given to these names, given to these circles, all of them are perceptual. It means that all of these circles that we have here are perceptual. Then since all of them are perceptual, means all of these circles consist of activation and linearity. It means that you have some information which comes from the previous layer. Previous layer send this information to this guy, and here when we receive this input, first linearity, then activation, and after that, something that we get after activation will be sent to the next layer. Yeah, please.
Can you remind us what the linearity?
Sure. Let's come back to the sure. Yes. And see, when we say linearity, means this. Then see, every neuron, every perceptron consists of this. This guy is called linearity. This guy is called activation. What is linearity? See, you have these numbers. These are numbers. Okay. You have these numbers. This guy is 1. These numbers can be anything. You have these numbers as the input. You will send these numbers to linearity. What linearity does, linearity multiply each weight to these numbers and add them. For example, W0 times 1 plus W1 times X1 plus W2 times X2 plus continue WD times XD. But chat, these W's are not known. These W's should be trained, should be learned. We will learn these W's. This part is called linearity. Activation is this guy. Any function here can be considered as activation. Here, for example, we have a step function, but there are plenty of other choices which can be used here. Then we combine these two and this guy is called perceptron. Historically, the first concept of perceptron was this. And after that, people, continue this with more complicated stuff. The only thing that we need to understand is that here, as we have these weights should be learned. You see, learnable weights. And this activation, you will choose activation. There are many activations, again, as we had before. You see, there are see, here, for example, are some activations which can be chosen. Any questions, any comments? Very interesting concept, actually, very interesting concept. Okay, so a little bit about the training MLP. During training the MLP, we will learn and adjust the weights. Okay, during training, because what should be learned, as Chad and I discussed, we have to learn weights. And as you can see, since you have plenty of layers, and you can have plenty of perceptrons, plenty of neurons, then there are many weights which should be learned. That's the reason that, as I explained several times, when you have MLP with many layers, training can be very time consuming. That's the reason that before 2010, this model was not very popular, because if you do not have powerful hardware, training can be very, very time consuming. That's the reason that after 2010 that we started working with more powerful CPUs, then these models got more interesting. So then we want to see that how these weights can be learned. During learning, the MLP learns to adjust the weights of the connection. When we say the weight of the connection, is that the weights that you can get on each perceptron between the nodes in each layer, in order to minimize the difference between predicted output and the actual output. Here, as you can see, we are defining the loss function, but the loss function that we define is not different to the loss function that we had before. It means that, again, at the end, you have the output, which can be found by considering the output layer, and that output will be compared to the actual values. That's the reason that, as I explained several times, neural network is a model which can be used for data set which is labeled. It means that you should have the actual label. Then actual labels are known, and you will get some estimated values by considering the output layer. Then you compare them. Comparing means that you use the loss function, and the goal is to minimize this loss function. So then how we can minimize the loss function? Again, as we explained for other models, here we will do the same. It means that one optimization algorithm should be used. For example, the only optimization algorithm that we learn in this class is gradient descent. But other optimization also can be used. Today we will see one of them. So that we didn't teach in this class. Therefore, you do not need to know the math behind all of this optimization. As many people who work in industry, they don't know anything about the math behind this optimization. I explained a little bit about math behind the gradient descent, but today we will see that there are plenty of different optimization. But as you can see, the procedure for all models is the same. It means that you have output. Output is the estimated value. You have the actual value. You will choose a loss function to compare actual and estimated value. You will choose the optimization algorithm to minimize this loss function. And the process of learning weights here can be done by minimalizing the loss function. Then, as you can see, process is the same as procedure that we had for other models. The only difference is that here the number of weights which should be learned is much more, comparing, for example, to easy linear function or easy linear model, or for example, easy logistic regression. Then something that we do here is a kind of generalization of logistic regression and linear regression. Something that we do here is just this. Okay, so then the model which is used, the method which is used for minimalizing the loss function is one model which is called backpropagation. What backpropagation means? Backpropagation means that you will start by input here. You will choose weights randomly. That's very important. Again, there is a paper which shows that if you choose weights, for example, all of them 0, you will terminate the process of learning. Then weights should be chosen randomly. Then you will start by input here. Input is given from your data. Weights will be chosen randomly for initial training. And after that, you will send inputs to the model. Then model will give you output. Here you have output by considering the weights. After finding this, then backpropagation tells us after finding this, then we will come back. And again, we will go forward. Then see, backpropagation is based on going back and forth. Let's see. Okay. So, in every time that we will reach to this, you will get output. Output is the estimated value will be compared to the actual value, and you will find loss function. When you find the loss function, then by considering the derivative of loss function, you will come back. And again, new weights will be learned. By considering the new weights, again, you will come back to this. Again, the actual value, estimated value, you will find the loss function. The derivative will be calculated by considering the optimization, for example, gradient descent. New weights will be found. Again, you come back. Then going back and forth, in every time that you go back and forth, then weights will be updated. And gradually weights will be updated, loss function will get minimalized, and step by step, we will get closer and closer to the better values for weights. Okay, I want to explain more about backpropagation. It has a little bit tricky math. The paper, I think, was established in 2013 about the backpropagation, and the math behind it mostly come from linear algebra and multi-dimensional calculus. Then math behind the backpropagation is a little bit complicated, and we don't want to go further. If somebody is interested, there are lots of good explanation about backpropagation, but I think it's a little beyond the border of our class. If you have a good background in linear algebra, you will find it easy. But if you don't have a good background in linear algebra, you may find it a little bit tricky. Yeah. So because it is based on the matrix theory and partial derivatives as well. Okay, so, but more or less this is something that we have for these layers. The only thing I want to say, then every time that we go back and forth, it is that we reach to here and we come back. Every time that we do this is called that epoch. Then the number of times that we want to go and come back is forward, backward, forward, backward. The number of times that we want to go forward and come back, backward, is called the number of epochs. And number of epochs can be chosen when you want to train. Okay, so then I think it's enough for theory. Let's see, less theory because I don't want to make it too complicated. It can be very complicated. So, okay. Let's come back to the model that we started last week. And I think for doing homework, the only thing that you need is this. So see, what we want to do here, we want to train a neural network with 2 layers. I'm talking about hidden layers, with 2 hidden layers, 1 output layers, and for sure 1 input layers. And in each hidden layer, for example, in the first hidden layer, we want to have 300 neurons. In the second hidden layer, we want to have 100 neurons, and then activations. Okay, I explained a little bit on Thursday about the hidden layers. As I explained on Thursday here, for example, in the hidden layer, when you want to assign a hidden layer on Keras, we will use dense. Dense means you are defining the fully connected layer. Then when you are doing homework, remember that when you want to consider the hidden layer, since the hidden layer should be fully connected, we will use dense. Then here, see, I am saying that I define a model as a sequential. When you have a sequential, it means that I have a sequence of layers. Then, and I add layers step by step. Then here, as you can see, one hidden layer is being added. Because it should be fully connected, then I'm using dense, the number of neurons 300, and activation. Activation here, for example, I choose relo. You can choose any other activation. So I strongly suggest you, when you want to do homework, check the help of Keras. In the help of Keras, then you can see lots of other activations. But if you use relo for your homework, I think it's okay. What about kernel initializing? In this case, as you can see, because you can say that, as we explained, when we want to start the process of learning, these weights should be initialized. You can say that in what way we can initialize. Fortunately, Keras will do this for us. Here, when we write kernel initializer, it means that we are telling to the Keras that use this initializing. He here is the name of guy, and it comes from the paper that he published, he and 3 other people. Then he here doesn't mean he, she. He's the name of person, okay? Then we have he, the name of the author of the paper. Paper was published in 2014, I think, 1314. That he suggested one method for, he suggested one method for initializing. After that, people started using that method. Here, when you write kernel initializing he normal, it means that you are telling to the Keras use that initializing that he suggested. Here, he means this, he, not he. Okay? And same story. Questions, comments? So, what about kernel regularizer? Again, in the homework, you can write this and you can skip it. But here, when you write kernel regularizer, because see again, as we explained, we want to see that if we want to reduce overfitting, what kind of regularization can be used? Again, there are plenty of different regularization which can be used here for reducing overfitting. Here we are using L1. See, there are many maths behind these two. But if you don't know anything about them, you can just use Keras. You can see how much Keras is powerful. Okay, then that's the first. Yes, Jack.
The first line after you define the sequential model is adding the input layers, right? Based on the.
Do we flatten? I will explain about that. Be patient. I didn't say anything yet about flatten. Be patient, please. Okay. I am just explaining right now, and last week I just explained about hidden layer. For input and output, I didn't say anything yet. I will explain it today. I will explain it definitely today. About flatten and about softmax. I didn't say anything about that yet. So then just hidden layers. Then see, this guy and this guy are hidden layers. Okay, so, but what about input layer and output layer? This is input, this is output. What input means? Here we said that flatten input shape 2828. Why we use this? Guys, see, here my goal is to use this model on pictures. Pictures have some pixels, right? Then when you have a picture, what do you have exactly? Let me show you. See, when you have a picture, you have pixels. For example, something like this. Suppose you have 28 by 28 picture. Then you have a bunch of pixels here, right? 20 by 20. Pixel. So, you cannot give this input to your model because your model just accepts the vector. How we can vectorize these? When you want to vectorize this, it means that you want to write this as vector. When I'm saying that writing as vector means, for example, you will list all of these, then this, and the second column will be written below, right? Third column will be written below, and continue, right? This process is called flatten. Then when we have flatten means this, means input is picture like this, you want to vectorize it, see like this. And you need to tell to Python that what is the output dimension. That's the reason that in the code that we have in Python, you can see that we have flattened 28 by 28. It means that I want to tell to my model that, see, input is a picture which is 28 by 28. When I run flatten, it means that I am telling to the model that converts this input to this vector. Make sense? Make sense? When you are doing homework, remember that you should do exactly the same thing if your input is a picture. If your input is not the picture, it's not necessary. It means that if your input already is a vector, then you already have vector. If your input is not vector, you should do this. Any questions? Any comments? For example, in the homework that you have, you want to use this model on the data set that we had before for SVM. Remember that? Then it's a good question that again, flatten is needed or not. Yes, question.
So when you train the model, you give it many pictures at the same time with their...
Exactly, that's actually the beauty thing. It means that you just need to run this for every single picture. You can do this for many pictures, and I will explain. I have not trained yet. The only thing that I did when we run flatten is when I'm telling to the model that, see, we want to use this model on pictures, but pictures should be vectorized. I'm vectorizing using flatten to get a vector. Yes, Chad.
In the code, why did you have to define the kernel initializer for the input layer?
Why we don't need to use this one for? Because in input layer, nothing actually, no weight in the input layer. Weights are in the hidden layers. In the input layer, you have just features which are given as the input. Then when you use, let's see, you start, okay, that's a very good question. Let me see. So. Okay, chat, see, look at these links that we have here. Links here has weight. It means that weights are related to these links. Because as we explained before, for example, when you consider this guy, then see, some xi values come from the previous layer, you will use weights here. Then weights should be assigned to the layers that contain weights. That's the reason that we are initializing on the values that contain weights. Then if we come back to the model, then see, that's model. In the model, as you can see here, we have weight, we initialize. We have weight again here, we initialize. The cases that you have weight, you initialize. When you have no weight, then nothing. No initializing. Here, then see, that's the input layer. I am using flatten. Why flatten? Because I want to say that we need vector. And this is 28 by 20 because I want to use this for pictures which are 28 by 20. More precisely, we want to use this model for means data set. Means data set are pictures which are 28 by 20. That's the reason that here we are relating. So, see, this batch normalization can be skipped if you want to. We do not have time, unfortunately, to explain about batch normalization, but very quickly, what batch normalization does, we use batch normalization for normalizing the way that neurons are assigned. But we need one lecture about this. Then I suggest you for homework also use this. The only thing that we need to do, the only thing that we need to know, batch normalization means that you want to tell to your model that use neurons in a nice way. Use neurons in a nice way. In order to make sure that our model is considering neurons in a nice way, my suggestion is that after input layer and before output layer, use the batch normalization. It can make the process of learning better, faster. And the last one is the output layer. Guys, see, in the output layer, again, I am using the fully connected. How many neurons? 10. Why 10? Because I want to use this model for classification on means data set. And as all of you know that in the means data set, you have data set of pictures which are labeled by 10 digits, right? 0, 1, 2, 2, 9. Therefore, here I am using 10. What about activation? As we explained before, if we use, for example, sigmoid, if we use, for example, sum, for all of those, output is just 2 cases, 0, 1. But in this case, we need output which has more than 2 outputs. In this case, we will use softmax. Again, there is lots of math behind it, but the only thing that we want to say is if your output has just 2 cases, we will use sigmoid. If your output consists of more than 2 cases, we will use softmax. Then softmax is the activation for cases that your output consists of more than 2 cases. In this case, if I had 2 here, I would write sigmoid. But since I have a number more than 2, I will write what? Softmax. In your case, in the homework, what number is needed here? 3. Thank you. Therefore, here, activation is softmax. Any questions? Any comments? Any questions? Yes, please.
Could the output layer could maybe just have a single node, and then the value of that node is 1, 2, 3, 4, 5, 6, 7, 8.
Exactly. For that case, it means that if we have that one, again, for this one, when we have this, you can write dense. 1 activation is again sigmoid. Activation again sigmoid. Exactly the same thing that we had for the previous problem. For the previous one, I mean the one that we use sign. Patrick and all, these models that I have posted on Carmen are very good for playing game to give the idea how to do homework. Then I strongly suggest you before doing homework, play a little bit game with these, then solve the homework. So, questions, comments? Now, and when you do the same thing at home, please again make sure that to see the summary of your model for the homework. Then see, we will run the summary of the model. Then when you run the summary of the model here, as you can see for the flatten, then we have these. How many parameters? 0, because for flatten you have no parameter, no weight. But here, see, we will go to the batch normalization. In the batch normalization case, that's the number of parameter. For the dense case, that's the first output layer. Then see, for the first output layer, this is because in the first output layer, you have 300 neuron. That's the number of parameters which should be learned. For the batch normalization, again, that's this one. Again, unfortunately, we don't have time to talk about batch normalization. Batch normalization is, again, we need one more lecture. And I think we just use this for making the output nicer. But something that I think you need to know is that these are not learnable. These are learnable. And same story again for the second output layer. For the second output layer, as you can see, that's the number of learnables. Again, batch normalization, and this guy also is learnable. And here, as you can see, total parameters, trainable, non-trainable. These are the values that we train to learn. These are the values which come from batch normalization, and we do not learn them. Okay, that's a summary of the model that we want to train. So now for training, you need the data set. Data set that we will get here comes from fashion mean set. The fashion mean set is a little bit different mean set. Actually, instead of having the 0, 1, 10 here for the fashion, we have some pictures. Let me show you this. I thought I had a fashion mean set somewhere. No. Then let me show you in the fashion mean set. Let me see. Okay. Yes, see? Yes. In the fashion mean set, instead of having 0, 1, 2, 10, something like this, you have the pictures of some clothes. Then you have pullover, trousers, bag, what 10. In this case, for example, so you have different pullovers, but pullovers are labeled by 2, t-shirt top are labeled by 0, and continue the trousers by 1. Then you have 10, you see, 10 classes of clothes. That's the reason that here again, as you can see, we use 10. Okay. Okay, so now we will get for validation and for training. Here, as you can see, we get this for training. We are considering this part of data set for training. Why we divide by 255? Because we want to normalize these. The same story for y values. Here, these are x values. These are y values. This is something that we did for other data set. I think it's not big. Okay, this part is important. We are doing this for compiling. For compiling, first you need to choose the loss function. As you can see, the loss function that we have here, we didn't see this loss function before. Always, when you use softmax, one of the loss function which is used very often is cross entropy. Therefore, the loss function that we have chosen here is a categorical cross entropy. In the homework, you will do the same thing, because in the homework, you will use again softmax. Optimizer, that's the optimizer that we didn't talk about. As I explained before, gradient descent is not the only optimizer that we have. Here in this case, as you can see, we are using RMS prompt. I strongly suggest you that you look at the help of the Keras to choose the different optimizer. And I think that's, let me see, show you what I'm saying, Keras optimizers, then see. Then see, then compiling feeds, then see. That's the optimizers that we can choose. I am using this one, then see, RMS from. This guy is gradient descent. This guy is Adam B. That is Adam. These are all optimizers which can be used. And if you want to see what they are, you just need to click on them and see code about the Atom. Atom is very popular. The paper of Atom was given in 2015. And after that, people use it a lot. Anything that you need about Atom is here. Keras has very powerful help, actually. For example, gradient descent. Let's see. And here, learning rate, momentum, Then examples. That's fantastic, actually, help. One more time, you can use this is RMS prompt that we are using. You can use Keras without knowing any math behind it. All of these optimizers that we have here, there are a very tricky math behind them. But see, without any math, you see, and everything that we need is here. And when you are training at home, if you see that, for example, by using RMSP, your training is not good, you can choose optimizer. And you can choose optimizer from here and then train. Then please play game, guys. Then when you train your model at home, please choose. And let me show you, for example, loss, to see that how many loss we have. For example, Keras loss function, Keras losses. And see again. Losses, let's see, available loss, let's see. We are using this loss here, cross entropy, but many other loss here. For example, binary cross entropy, If you click on these, they make everything that you need here. With examples. That's very, very helpful, I think, especially when you are doing homework. I strongly suggest you do this, then to change and train one more time. That's very helpful to give you the idea that what you are doing. It means that here, when you want to write things, something that we had. Okay. So, see, something that we had last semester when Gradle actually told me about this. Some students, because we had exactly the same thing. I taught Keras and after that we had the homework. Some students used exactly the same compiler that I gave them. Okay, it's good, but be a little bit creative. You have help of Keras and you can change them and train one more time. That would be very helpful when you see that the change of, for example, loss can make the process of learning sometimes faster or more slowly. I think that's very interesting. Then please do. And then see here, for loss, we use this one, and metric that we use is accuracy. For your case, again, accuracy should be used. Now, compared to something that we did before, when we wanted to find accuracy, we needed to write some lines of the code, but here it's not necessary. That's just we did give a metric. And again, there are plenty of metrics. Then, again, Keras, metrics, Keras, then metrics, accuracy metrics, probabilistic metric, regression metrics. That's fantastic. No, classification metrics. That's amazing. Image segmentation metric. Help of Keras is very, very powerful. And believe me, in many cases, something that we teach in a class is not even 10% of help of Keras. Even in deep learning courses, this is something that people learn through working with this. Then that's something that I told you, that people who are in the industry, they don't know anything about math. Something that they know is that by their experience, gradually they will find out, for example, for their purposes, this metric works better. Okay? Again, for all of these metrics that we have here, there are plenty of tricky math behind them. But you don't need to know anything, just using and choosing and using. That's it. Okay, so any questions, any comments? Then, as we explained before, you have to consider the learning rate. I think the discussion that we had before about one of the extra credits, I think Patrick and maybe another student, we talk about learning rate and we change learning rate and we train again and we got better. Then here, as you may remember, somebody told me that how learning rate should be chosen. That's one way to choose learning rate in a nicer way. What we are doing here, we are initially, that's one of the very interesting technique that we have in the Keras for choosing learning rate better. Here we have the LR here. Okay, this is the name that I have chosen. This is LR, stands for learning rate schedule. You have Keras optimizer scheduling exponential decay. Then see, you choose learning rate, one initial value for the learning rate, and step by step you will adjust learning rate. Here I am saying that you choose this guy as the initial value, and by this amount of steps, choose learning rate, adjust learning rate, and as here you can see this is a decay rate. Here we are making learning rate smaller. That's one process to make learning rate, to choose learning in a nicer way. Because as we discussed before, for example, extra credit number 3, by choosing learning rate, you could make the process of learning better. Then that's something that we do here. That's fantastic. Again, guys, please play them here. Then change the steps, change this, and then you can then train, then you will find it very nice. That's very, very nice. Okay, so then now we can say that, okay, we want to use optimizer RMSP. Learning rate is the learning rate schedule that we have on the top. Then everything now is ready for compiling. Then here we choose everything that we need are ready for compiling. Optimizer is chosen. and here optimizer that we define here. The only thing that I did here is instead of choosing RMSP with the given learning rate, I am using RMSP with the learning rate which is chosen, not the fixed value. It means the learning rate is changing. And after that, we are training the model. Here, when you want to train the model, you have to, this is a model that you define. Then we use .fit, training, X and Y, number of epoch, 30, you can choose it. Validation, here you can say that choose these two for validation. And now you are running this. Then see, for every epoch, loss, accuracy, validation accuracy will be calculated simultaneously. You don't need to calculate anything. That's amazing, isn't it? Then see, the first epoch, loss is 2.3, accuracy is 70%, and that's the loss that you get on the validation. That's the accuracy that you get on the validation. What I did, I splitted my data set into two parts. One of them is being used for training, another is being used for validation. So then here you will get two losses, one of them for validation, another for training data set. Then here, as you can see, this is accuracy that you get on the training data set, means the data which is being used for training, you get accuracy on that data. And this is the accuracy that you will get on the validation. It means that simultaneously, Keras will compare the values that you get as the output with the training data set and in the validation data set, and gives you the loss and accuracy in the same time for every epoch. See, there are lots of math here, but you don't do anything. Everything is being done by Keras. You don't do anything. Any questions? Any comments? Yes, sir.
So the validation data is the same as the testing data?
Exactly. In here we use val cost, but because this is something that which is used in Keras. But it's completely the same. Validation is completely the same. Questions, comments? Then see, first epoch, loss is this. Accuracy is 70%. We will run one more time, loss get this. See, do you see that through the epochs, loss is getting smaller and smaller, see? You want to have, okay? It is a little bit time consuming. That's the reason that, when you do this at home, be patient, guys. So then here, see, as you can see, through the running through epochs, when you train through epochs, as you can see, loss is getting smaller, validation is getting better. This is something that we expect when you run at home. If you notice that, for example, your loss is not getting small very well, then it shows that some stuff should be changed. For example, you can change the initial value that you have chosen for the learning rate. You can choose the number of, for example, nodes that you consider in each layer. These hyperparameters should be changed to make the process of training better. But see, when we are going deeper and deeper, you can see that loss is getting smaller and smaller. After running for 30 epoch, that's something that we got here. Loss is 1.1, is still not very good, but accuracy is not bad. Accuracy on the training is 80%, that's not very important. Accuracy on the validation also is 80%. It seems that we get not very good accuracy, not terrible accuracy. So, something that I would do, I would choose the more epoch, but remember that choosing more epoch is dangerous. Because if you get more epoch, it is possible that you will end up with the overfitting. But my feeling is that still here we have something, we have some underfitting. Because here, as you can see, loss still is not good enough. Accuracy still is not good enough. Therefore, we can choose bigger epoch to train more. And if we feel that we are getting the better loss for both, then it seems that the model is not training bad. But if we still have bad numbers for validation loss and training loss, it seems that maybe we need to change some stuff in our model. One more thing, while we are calculating both loss, this loss will give us underfitting, this loss give us overfitting. Then it means that here it seems that still we have some underfitting. Therefore, it's better that to train more. It means that more epoch. Any questions? Any comments? Hope it gives you the idea that what should be done for this homework. For this homework, you will do more or less the same thing. But again, many things should be adjusted then when you train. And good luck with the homework. I hope you like it. So here we have gradient clipping. I don't want to explain about this, and this guy for transfer learning of image recognition. I don't want to explain about this. I think mostly this stuff is used for more deep learning forever courses. Then I think something that you need for the homework is just here. If somebody is interested, you can look at this stuff. Especially this, which is convolutional neural network. We didn't teach convolutional neural network, but intentionally I wanted actually to put some code about this if somebody is interested. And see, load. And inception is another model that we didn't cover it. This is actually one very famous model in deep learning. So if somebody is interested, but something that you need for the homework is just until here. Okay, so that's it for Keras, but as I explained several times, something that we did in this class for Keras is do a small, then there are lots of things ahead, then I hope you like it. And good luck with the homework. I'll be in office, any questions, and if you need my help, please stop by my office. I'll be more than happy to help. And something that I want to say one more time, guys, please don't use exactly the same code that I posted. Then be a little bit creative, change some stuff. And because one student, as I told last semester, he stopped by my office and said that I use the same thing but not a good loss. Okay, then change some stuff. It shows that some stuff should be adjusted. Then please do. Okay, so the last thing that we want to see a little bit about this is dimensionality reduction. And then see, one issue that we have is we have a data set which contains many dimensions, but all of them are not helpful for us. The interesting question which should be answered is how do we know that what dimensions should be kept, what dimension should be ignored? That's a very good question. Suppose, for example, you have a data set with 3 million features. How we can say that mathematically which dimensions are helpful and which dimension can be skipped? So then one important topic that we have in machine learning is called curse of dimensionality. Means that how we can fix the issue of dimensionality. Let's see some definition. Many machine learning problems involve thousands of, even millions of features for each training instances. So then note, not only this make training extremely slow, but it can also make it much harder to find a good solution, as we will see. It means that when you have a training data set which contains millions of features, yes, some of them are helpful, some of them are not helpful, and if you consider all of them, you can have very slow model. And it is possible that you do not reach to the good solution. Therefore, that is a very good question, that how we can ignore part of the features that we have. How we can say that what features are more important for us and we keep them, and what features are not very important, we can skip them. So this problem always is referred to as curse of dimensionality. When we say curse of dimensionality, means that we want to fix the issue of dimension and we want to understand what features are more important than others. So apart from speeding up training, dimensionality reduction is also extremely useful for data visualization. We do not cover this in this class, but that's a big part of the deep learning models. And you can see that when you really use the dimensionality, sometimes you can see that you have some pictures that when you consider all dimensions, you cannot visualize picture very nice. But when you omit when you ignore part of the dimensions, part of the features, you can see that the data gets more visualized. The data can be visualized better. Okay, so then let's see one example. Consider, for example, means image. The pixel on the image border are almost always white. So you could completely drop these pixels from the training set without losing much information. This is one example, I think very nice example. I have stolen this from the book and it's a very, very good example. Because several times students ask me how it is possible that some features are not helpful. Some features are not very necessary. We can skip them. This is a very good example. In the means data set, when you consider borders for all pictures, borders are white. Therefore, if you skip them, then you do not miss anything. That's one very good example that how some features do not give us lots of important information, and if you ignore them, you do not miss a lot. Moreover, two neighboring pixels are often highly correlated. Yes. Then if you merge them into a single pixel, for example, by taking mean of two pixel instances, you will not lose much information. That's, I think, very, very good example of how dimensions can be reduced. Suppose, for example, you are considering two pixels which are neighboring. These are very correlated, right? Therefore, if we take average of those and we define a new dimension, instead of having two dimensions, we combine them by taking averaging, and now we have one dimension. See, we are reducing the dimension. But by doing this, we do not miss lots of information, because you have two neighboring pixels which are very correlated. When you combine them by taking averaging, then here you are reducing the dimension and you do not miss lots of information. Yes, Chad, please.
Would this be done before you instantiate the input layer?
Yes, exactly. Yes. Then the test of dimensionality actually is one process which is used for cleaning data. Cleaning data not meaning cleaning, means making data more usable. Then yes, this process, of course. And case of dimensionality is the one technique that mostly is taught as a unsupervised learning. Because as we explained, we have two types of learning, unsupervised and supervised. Case of dimensionality and clustering are two techniques which are classified as unsupervised. These are unsupervised. And we do this stuff before the process of training. It means that people use case of dimensionality, make the dimension, reduce the dimension of the data set, then they use the data set for another purpose, for example. Here we want, I just wanted to explain that what does it mean when we say that some features are less important than others. I think these are two very good examples, actually, very practical examples. Any questions, comments? Okay, there are many techniques for reducing the dimension. One of them that we will cover in this class is called PCA. PCA is an abbreviation, Principal Component Analysis, and PCA is a linear technique. So PCA is used very often. I can say that one of the most popular techniques that we have for reducing the dimension is PCA. There is a pure math behind PCA, which comes from matrix theory, which is called this singular value decomposition. Singular value decomposition, if you took linear algebra, then you may have seen this. Then this is the one technique that we have in linear algebra. It comes from pure linear algebra. But if we don't want to see this, we want to see PCA without using this math, because PCA can be explained in a very nice way without using lots of math. But let's say a little bit about PCA. In most real-world problems, training instances are not spread out uniformly across all dimensions. So then many features are almost constant, while others are highly correlated. We had this about means, and for other data sets, we may have the same thing. As a result, all training instances actually lie within a much lower dimensional subspace of a high dimensional space. Which means when you have a data set which has million features, there are some features which are more important than others. So, in other words, there are some dimensions which are more important than others. The goal is to consider those, and the goal is to project on those dimensions. That's something that we want to do. So, let me explain this. Then see, suppose, for example, you have a data set like this. In this data set, as you can see, you have 3 features, x1, x2, x3. You have a 3-dimensional data set, x1, x2, x3. What we want to do, suppose we will find out 2 features which are more important than others. By using those features, you can consider a plane, and when you consider that plane, all other data points will be projected on this plane. And what you are doing when you do this, you are reducing your data set from 3-dimension into 2-dimension. So, a little bit math. Why 2 vectors here are found? Mathematically, when you want to find the plane, you have to find 2 vectors belonging to the plane. Because in mathematics, every plane can be found by 1 vector perpendicular to that plane. That vector is called normal vector. And when you want to find the plane, if you have 2 vectors belonging to that plane, the normal vector can be found as a vector which is perpendicular to the both. And when you find that vector, the plane will be found. Therefore, when you have 3-dimension, the goal is to find these 2 vectors. When you have these 2 vectors, what these 2 vectors have, these 2 vectors contain more information than other. It means that these 2 vectors are 2 vectors which contain the majority of information. These are the more important other than 3 vectors. Then when you find these 2 vectors, then what you will do, you will find this plane, and when you have the plane, you will project everything on the plane. By doing this, you are reducing the dimension. It means that after projecting, now you have a data set which has 2 dimension, not 3 dimension. A little bit tricky if you don't know these vector stuff, but don't worry about this. The only thing that if you don't know vector and those math stuff, the only thing that we need to understand is that you have data set, we will find the plane, how, forget about this, then we project on the plane. So, when you project, then see, you get something like this. Let's see, Z1, Z2, then see, here you have a 2-dimensional. After projecting, now you have something like this. You have started with a data set with 3-dimension, you found this Z1, Z2, now you project, then you got this data set. Let's see, 2-dimension. What I did, I reduced dimension, right? There are lots of questions here. Someone can say how you got Z1, how you got Z2. Yes, lots of dimensions, lots of questions here. There's a math behind it, how Z1 and Z2 can be found, but forget about those. The only thing that we need to understand is that by using some math techniques, Z1 and Z2 can be found, then you will get a plane, 2-dimensional plane, then you project everything on a 2-dimensional plane. So, projecting always is not the best way for reducing the dimension. It means that if you have a data set like this, in this case, if you project, you do not get something nice. It means that sometimes after projecting, it is possible that you miss lots of information. PCA is a technique, because see, the most important question which should be answered is how Z1 and Z2 can be found. PCA is a technique to give us how Z1 and Z2 can be found. PCA is an abbreviation for principal component analysis, is by far the most popular dimensionality reduction algorithm. It's used very often in machine learning, but we have more techniques, but PCA is very popular. So before you can project the data set onto a lower dimensional hyperplane, you first need to choose the right hyperplane. A right hyperplane means you have to choose what Z1 and Z2 are the best. And in order to answer this question, we need to use the concept of PCA. Then here, see, this is one example of the case that you can project on, you have the data set which is given with 2 dimensions. You want to reduce the dimension. When you want to reduce the dimension, you have to project on a line. This is a given data set. You want to reduce the dimension. Since the given data set has 2 dimensions, when you want to reduce, you have to project on a line. Because when you want to project on a line, after projecting on a line, you will get the data set which has just 1 dimension. Now the question is, what line should be considered for projecting? We have this line, we have this line, we have that line. Many lines can be considered, right? The only thing that we can say is, this is a given data set. I want to find the appropriate line. I want to project on that appropriate line. But the question is, what line is appropriate? There are many lines can be drawn here, right? I have just some of them here. And many others can be found. Okay? Question? Comment? So, here I have some lines after projecting. I projected on that line, that's the number of data that I got. I projected on another line, that's the data that I got. I projected on another line, that's the data that I got. Which line is better? I believe the first one. But why the first one is better? What's the difference between the first one and the third one? Yes, please.
The first one is giving more information.
Give us the more information. But if you want to have a more mathematical concept for understanding what more information means, what's the difference between 1 and third? Variance, thank you. As you can see, the first one has a higher variance. The last one has a smaller variance. And if you want to translate something that Mehran told us, because when Mehran says that, okay, the first one gives us the more information mathematically means bigger variance. Then see, the first one has the biggest variance, this one has the smallest. Therefore, among the lines that you can choose and you can project on them, we choose the line which gives us the maximum variance. You can have plenty of lines, but we will choose the one that after projecting you get the maximum variance. Then here we can see that the first one is better, because the first one gives us the maximum variance. This is the foundation of PCA. That's it. Any questions, any comments? I try my best not to give you lots of math. Again, lots of math behind it, but that's the foundation of PCA. PCA tells us you can draw lots of lines and you project on the line. Among these lines, we choose the line which gives us the maximum variance. And that's the best. Any questions? Any comments? Question? So, the idea behind PCA is something that we have seen. That it seems reasonable to select the axes that preserve the maximum amongst the variance, as it will most likely lose less information than other projections. Another way to justify this choice is that it is the axis that minimalize the mean square distance between the original distance and its projection onto that axis. I think this is a foundation of PCA. It means that you want to get how we can find axes Z1, Z2. We can say that there are lots of lines which can be considered. We pick the one which has the maximum one. The only thing that I want to say, someone can say that, okay, it is good for the case that we have two-dimensional data set. What about if we have three-dimensional, for example, something like this? In three-dimensional, what we can do? In three-dimensional, you need to choose these 2 lines. How I got these 2 lines? This line is the line which has the maximum variance. This guy is the line which has the second maximum. That's easy, isn't it? If we have 4 dimensions, what we will do? We will pick 3. The first maximum, second maximum, third maximum. And you can continue. Then if you tell me, for example, you have 5 features we want to reduce to 3 dimension. What we will do? We will choose axis. The first axis contains maximum variance, second axis, second maximum, third axis, third maximum. And you will get those axes that you need, and you get the plane that you can project on. Questions, comments? Any question? These axes that you consider that contain the first maximum, second maximum, third maximum, go to this maximum are called component, principal components. Then these principal components that we are talking about are these axes. The only thing that you need to remember, these principal components should be orthogonal. That means they have to be perpendicular, okay? And these axes will give us the plane that we want. No math, as you can see. Okay, that's something that we need for this class. As you can see, I try my best not to give any math. If somebody is interested in the math behind it also explained, then it's going to be the matrix theory. So as you can see, tricky math, a little bit tricky math. If you are interested in linear algebra, you will find it not very hard. But if you are not very interested in linear algebra, you may find it a little bit tricky. Because something that we do in general is this maximalization. So there are, again, if somebody is interested, there are beautiful videos on YouTube. One of them that I really like about this, I've seen several videos about PCA. One of them that I really like it. There is a person who is in Canada. His name is same as mine, Ali Otsi, okay? The guy has a video there about this, and I really like the video that he explained. And if you are interested, please watch his videos. His students actually published, they publish all of his lectures, and I think he has started lecturing, I think, since 2015 until last year, about machine learning, about deep learning, and some of them are really good. But I should warn you, you should be a little bit good at math, because lots of math. And he explained. But if you want to see the math behind PCA, especially this stuff, and I think his lectures are fantastic, very good, and I really like them. So then, if somebody is interested about math behind them, then look at his lectures. And this is read his notes, then look at his lectures. I'm sure that you will find it you will understand this very well. But if you are not interested in math behind this, don't worry about this. As I explained, I tried to divide this slide into 2 parts. The first part, no math. Second part, more math. Okay, I think it is a good time to, yes, please.
You mentioned projection is not always the best approach, but is there any condition or something like that?
So when we say that projection is not very good, is distance. See, when we want to projecting means this, means you have some data sets, and you want to project on something like this, flat. Sometimes it works very well, but suppose your data set is look like this. Something like this. In this case, if you use a flat space, I don't think so it works well. Someone can say that while you use flat space to project, let's use a space like this. In this case, projecting gets better. It means after projecting, you get the better results. But PCA means always we project on flat spaces like this. But we have something more complicated than PCA, which tells us instead of projecting on flat space, like let's project on this. Mathematically, these flat spaces are called Euclidean space. Where we have something like this, it's called manifold. Change. And it is harder, much harder. PCA is based on, but when here we say that projecting always doesn't work, it means that projecting on a flat spaces. Then see, PCA is based on projecting on a flat spaces. But projecting on spaces which are not flat can be, for data set like this, for sure works better. And there's a different type of case of reducing dimension. And you can see, I think in 2 lectures he explained about this, that how you project on a plane which are not necessarily flat. He's very good. he's very good at lecture. I think he did master in Shiroda. Okay, any questions, any comments? I'll be here, guys. Today is the last day of our class, so we don't have class on Thursday. I'll be available in the office. Please feel free to stop by if you need my help for the final project, for the homework. The homework, it is about Keras. It is due on Monday 22nd. We will be a little bit flexible. I will post also the solution. Any question, any comments, please stop by and have a good day. So then hope you have a good, nice summer. Then I'll be available in the office. Have a good day. See you all. No, not see you all. Have a good day. So, oh yeah, sure. So Reza, what is the due date of project? Because I don't remember, to be very honest.